Now that we've got citrate from the citrate synthase reaction, the next step in the citric acid cycle is a reaction catalyzed by aconitase. It's a reversible reaction where citrate is converted to isocitrate. Though your diagram in the book really shows it as a one-step reaction, I do want you to know that it's really a two-step reaction where aconitase first dehydrates synthase, it loses water and is converted to cis-aconitate. Right here, that's an intermediate, that's a transient, and then water is added back, again catalyzed by aconitase, and cis-aconitate right here is converted now to isocitrate because the water is added back in the opposite direction. So you lose water here, that OH and that H is lost as water, and the water is added back, but in the opposite direction, the OH goes here and the H goes here, and you end up with isocitrate. So let's look at this reaction in a little more detail. It's catalyzed by aconitase, and it's a two-step isomerization. We've seen that on the previous slide, of citrate to isocitrate. Why do you need this? Okay, it's because citrate is a poor substrate for oxidation. If you look at citrate right here, is this hydroxyl a good hydroxyl for oxidation? No, because it's a tertiary hydroxyl group and there's no H to remove, and so it's difficult to oxidize this hydroxyl group to a carbonyl. Okay, that's not good, so that's where cis-aconitate comes in. It converts citrate to isocitrate, and in isocitrate, you've converted a tertiary hydroxyl group to a secondary hydroxyl group. Is this a better substrate for oxidation? Excuse me? Yes, it is, right? I can remove that H and convert this to a carbonyl. I can oxidize carbon now. So that's why we get this reaction. Okay? Please do note that the stereochemistry of this reaction. In aconitase, when it converts citrate to isocitrate, actually removes a hydrogen here and this OH here. It removes a hydrogen only from the pro-R arm of citrate. Citrate is not chiral, okay, it's achiral, but it is pro-chiral, and it has this group right here and this group right here that are the same, but this is the pro-S arm because if I modify it, I get chirality, and this is the pro-R arm because if I modify it, I also get chirality because that carbon becomes chiral. So an important thing to keep in mind is that in the aconitase reaction, aconitase participates in pro-chiral differentiation because the double bond is only placed by aconitase on the pro-R arm of citrate. So it removes water to place a double bond in cis-aconitate only on the pro-R arm, and then water is added back by aconitase just in the opposite direction to give you isocitrate. The last thing to know about aconitase is that its reaction employs an iron sulfur cluster. It has an iron sulfur cluster in the active site that helps it catalyze this reaction. Here's actually a picture of that iron sulfur cluster. The irons are shown in green, the sulfur is in yellow, and as you can see, two cysteines in the active site help hold the iron, or help coordinate the iron as a part of the iron sulfur cluster. All you need, it's actually called a 4Fe4S iron sulfur cluster. I won't ask you to like draw it or something like that, but just know that aconitase has an iron sulfur cluster that helps it catalyze its reaction. Here's actually the mechanism of how that works, but I won't ask you to know that. I just wanted to put this in here for those of you interested in this kind of chemistry. And this has been mentioned before, aconitase exhibits pro-chiral differentiation. Here's citrate, you have the pro-S arm and the pro-R arm. Aconitase only places the double bond on the pro-R arm of citrate and only adds water back to it to give you isocitrate. Why is that? Because the active site of aconitase is chiral. Okay, and though citrate is achiral, it is pro-chiral because if you modify the pro-S arm, you get chirality at this carbon, or if you modify the pro-R arm, you get chirality at this carbon as well. So here's a kind of a tetrahedral model of that carbon right here of citrate. There's your pro-S arm and there's your pro-R arm. When you look at how this molecule, if you look at this carbon and these other arms coming off it fit in the active site of aconitase, only the pro-R arm interacts with the active site. The way these fit, only the pro-R arm interacts with the active site, and that is why the double bond is placed on the pro-R arm of citrate, and thus aconitase participates in pro-chiral differentiation. So please do know this about aconitase. The double bond is placed on the pro-R arm, and only the pro-R arm is modified to give when you get isocitrate. The next step in the citric acid cycle is catalyzed by an enzyme called isocitrate dehydrogenase. What does it do? Remember what a dehydrogenase is? A dehydrogenase is a redox enzyme, and it's removing an H- from something and transferring it to something else. So look for redox cofactors, look for H- transfer, and that's exactly what happens. Okay, you've got isocitrate, you get NAD plus involved as well, and that H as H- is transferred to NAD plus, to give NADH. And at the same time, an H right here is lost as H plus as well. Of course, what are you doing to isocitrate in this case? So what are you doing to the carbons of isocitrate in this case? You're oxidizing them, and in that process, you're harnessing that oxidation to make a high energy compound, in this case, NADH. So what carbon's getting oxidized? This carbon here of this carboxylic acid is getting oxidized and comes off as CO2. And this carbon right here, we just talked about this hydroxyl group on isocitrate. It was a poor substrate for oxidation in citrate because it was a tertiary hydroxyl group here. After the aconitase reaction, you have a secondary hydroxyl group, of course, which is a better substrate for oxidation. And that hydroxyl group right here, and that carbon that has a hydroxyl group gets oxidized to a carbonyl right here. So you get oxidation of carbon from isocitrate to alpha-ketoglutarate. That's what this compound is called right here. And you lose that carboxyl group as CO2, and an NAD plus gets reduced to NADH. So the energy captured of oxidizing carbons is captured as NADH, which has high energy electrons. So now let's look at the isocitrate dehydrogenase reaction in more detail. Remember, it's a dehydrogenase, it's a redox enzyme, there's hydride transfer involved. Look for redox cofactors as well. So here's what happens. It's an oxidative decarboxylation of isocitrate to yield alpha-ketoglutarate. Okay, it's classic NAD plus chemistry. There's hydride removal followed by a decarboxylation. So let's look at that. Here's isocitrate, that secondary hydroxyl group. There's a great is on a carbon that now can be oxidized. You first get that hydride transfer. That hydride here, remember it's a dehydrogenase. This hydride transfer, the hydride gets transferred to NAD plus. I get NADH. That H comes off as H plus. So I get H plus and NADH released, and this carbon gets oxidized to a carbonyl. That's your classic NAD chemistry there, that part of it. And the second part, you get your decarboxylation. This carboxylic acid group comes off as CO2, and there's your decarboxylation. The enzyme requires a manganese cofactor right here to help facilitate the decarboxylation. You end up with this intermediate that has an alkene here, but it rearranges. It's actually an enolate right here. An H plus adds on, and the enolate tautomerizes, and you end up with a carbonyl here, and you end up with alpha-ketoglutarate. What's the difference between alpha-ketoglutarate and isocitrate? You've oxidized this hydroxyl group to a carbonyl, and you've lost this carboxylic acid group as CO2, and you end up there with alpha-ketoglutarate. So you've lost a CO2 in the reaction, and you've also formed an NADH plus H plus from an NAD plus in this reaction as well. Okay, just something to keep in mind is because you formed an NADH here, what does it have? It has high energy electrons. So isocitrate dehydrogenase is a link to the electron transport pathway because it makes NADH. And we'll look at that, the electron transport chain and oxidative phosphorylation, like I've said later when we get to chapter 18. A very important thing to keep in mind about the isocitrate dehydrogenase reaction is that it's the most important regulatory enzyme of the pathway of the TCA, and it's important to keep in mind that it is activated by ADP, adenosine diphosphate. Please star this and keep this in mind. Why would you want it to be activated by ADP? When you're rich in ADP, it means you're lacking in ATP, because if you add a phosphate to ADP, you end up with ATP. So what does that mean? The TCA is an energy generation pathway. It's generating energy. If you don't have a lot of ATP, and you have a lot of ADP present, you want to activate the TCA, so you make more energy and you store it in the form of ATP, the energy currency of the cell. So that's a very logical logical thing to think that it is activated by ADP. Now let's look at the next reaction of the TCA, and this is catalyzed, by another dehydrogenase, and this is called alpha-ketoglutarate dehydrogenase, based on the substrate for the reaction being alpha-ketoglutarate. Again, it's a decarboxylation, an oxidative decarboxylation at that. what happens is this carboxyl group of alpha-ketoglutarate comes off as CO2. Again, you harness the energy of oxidizing carbon to convert NAD plus to NADH, a high energy molecule which has high energy electrons, which is can be used to make ATP. And in the process, it's also important to keep in mind this enzyme also includes or involves a coenzyme A cofactor, and the CoAsh or coenzyme A cofactor right here adds to this carbonyl, and you get a coenzyme A derivative called succinyl-CoA as your product of the reaction. So let's look at this in a little more detail. It's a second oxidative decarboxylation. Here's alpha-ketoglutarate. There's CoAsh. The S here adds on. I get succinyl-CoA. I get a CO2 released. I get the energy of the oxidation of carbon captured by NAD plus being reduced to NADH. This reaction, as you can see, is one directional, right? So it's an irreversible reaction, and this is the main reaction that makes the cycle, the TCA, unidirectional and turn in the direction, the clockwise manner shown in this picture. As you can see, it's turning in a clockwise manner shown as illustrated, and this reaction right here, the alpha-ketoglutarate dehydrogenase reaction, is the main reaction that makes this irreversible and turn in this direction as written. A little side note, let's look at some other reactions. Is the isocitrate dehydrogenase reaction irreversible? Yes, right, there's a one directional arrow here. It too is an irreversible reaction. When I say a reaction is irreversible, like the isocitrate dehydrogenase reaction or the alpha-ketoglutarate dehydrogenase reaction, what does that mean? That means that it is a highly exergonic reaction. So both reaction 3 catalyzed by isocitrate dehydrogenase and reaction 4 catalyzed by alpha-ketoglutarate dehydrogenase, both are highly exergonic reactions. They go in one direction, and this one, reaction 4 catalyzed by alpha-ketoglutarate dehydrogenase, is the main one that makes a TCA irreversible in flow in the clockwise direction as it's drawn in. Now here are a few more important things to point out about alpha-ketoglutarate dehydrogenase. Just one more thing, instead of saying dehydrogenase from now on, I'm just going to say DH for short. So please know, when I say DH, I mean dehydrogenase. So DH means dehydrogenase. So let's look at a few facts about alpha-ketoglutarate DH. It actually is in fact a large multi-enzyme complex, and here's what's interesting. This is a complex that's nearly identical to pyruvate dehydrogenase, or PDH, and it's both identical structurally and mechanistically to PDH. So we've seen this picture before, right? And we've seen it to represent the PDH multi-enzyme complex, and in fact alpha-ketoglutarate DH also looks like PDH and has the same mechanisms as PDH as well. So it's similar both structurally and mechanistically to PDH. Please make sure you know that, okay? Please, that's an important point. Please start this point and make sure you know it. But it's got different substrates. Instead of pyruvate being the substrate, which pyruvate of course is a substrate for PDH, instead for alpha-ketoglutarate DH, its substrate is a longer coenzyme A derivative. It's actually alpha-ketoglutarate right here. Instead of pyruvate, you've just got this longer group right here. And here, its reaction is very similar to the PDH reaction. You have CoAsh. CoAsh, you get a carboxyl group leaving as CO2 like we saw for PDH. NAD plus gets converted to NADH like we saw for PDH. And the CoAsh makes a bond to a carbonyl to give you a coenzyme A derivative. But instead, in PDH it was acetyl-CoA. Here, for alpha-ketoglutarate DH, we have succinyl-CoA. So, what does this mean? It means that alpha-ketoglutarate dehydrogenase is specific for longer coenzyme A derivatives. It's specific for alpha-ketoglutarate instead of pyruvate. Again, if it's mechanistically and structurally similar to PDH, we've saw that PDH requires these 5 coenzymes, TPP, CoAsh, lipoic acid, NAD plus and FAD, and thus alpha-ketoglutarate DH also requires the same enzymes. And as you can see, it's an irreversible reaction as well, okay? And that's why this is the main reaction that makes the cycle unidirectional, because this reaction is irreversible. And a little take-home about this is oftentimes when you have a decarboxylation in biochemistry, that reaction is you can't go back on. It's normally or usually an irreversible reaction. So this is an irreversible reaction, and we saw as well for the previous reaction in the TCA, the isocitrate dehydrogenase reaction as well, it's a decarboxylation as well, and so it's a irreversible reaction as well. So in general, not always, but for most of the time, decarboxylation reactions are irreversible. So please make sure you know these points about alpha-ketoglutarate DH. These are important points about it. So just looking at comparing the two reactions, here's the PDH reaction. Pyruvate, CoAsh, CO2, CoAsh comes in, you get acetyl-CoA. This carboxyl is lost as CO2. NAD plus gets reduced to NADH plus H plus. That's the PDH reaction. It's a large multi-enzyme complex. Here's alpha-ketoglutarate dehydrogenase. It's just a different substrate. Instead of pyruvate, you have just a longer substrate, alpha-ketoglutarate right here. CoAsh comes in, makes a bond to this carbonyl, just like we see right here. This carboxylic acid group comes off as CO2, so it's an oxidation reaction. And in that oxidation, energy is harnessed by reducing NAD plus to NADH, just like we've seen here. So you can see these reactions are very similar, but just the substrates are just a little different. And you end up with two coenzyme A derivatives as products, but for PDH you end up with acetyl-CoA, just a 2-carbon group, and for alpha-ketoglutarate DH you end up with succinyl-CoA, where you have 4 carbons with the carbonyl attached to coenzyme A. So please keep this in mind. Please know that alpha-ketoglutarate DH is similar structurally and mechanistically to pyruvate dehydrogenase. So here's the PDH reaction, right? The five reactions, 1, 2, 3, 4, 5 involved in the overall. These reactions all contribute to the overall reaction of the PDH complex, which you've already seen this before. So thus, for alpha-ketoglutarate dehydrogenase as well, its reactions will be very similar, but instead of pyruvate right here, you'll just have alpha-ketoglutarate right here instead of pyruvate. So it'll look just like this. Instead of pyruvate, you have alpha-ketoglutarate right here, and all the reactions will be just like the reactions of the PDH multi-enzyme complex, but just your substrate will be a little longer, and you end up with succinyl-CoA as a product instead of acetyl-CoA. So here's the overall reaction. Alpha-ketoglutarate plus coenzyme A plus NAD plus gives you succinyl-CoA plus CO2 plus NADH. And all the stuff we've learned about the cofactors in the PDH reaction we've seen here also apply to the cofactors in the alpha-ketoglutarate DH reaction as well. So it looks like pyruvate dehydrogenase and reacts like pyruvate dehydrogenase, but just for a different substrate, alpha-ketoglutarate instead of pyruvate. Please keep that in mind.